Harvard astrophysicist Avi Loeb has just released an analysis suggesting that 3 Atlas might have catastrophically exploded into at least 16 fragments, creating a cosmic fireworks display we're only now beginning to witness. This isn't speculation. The evidence is real. The data is quantifiable, and the implications are staggering. Think about what that means. We're potentially watching the fragmentation of an interstellar object in real time. We are witnessing evidence of its disintegration captured through telescopes and space-based instruments. But that's where the official story starts to get complicated, because there's another possibility, one that raises even more unsettling questions about what this visitor truly is, and the clock is ticking to find out which narrative is correct. Let me walk you through the evidence. This story begins not with the explosion, but with an impossible observation made months before perihelion 3 Atlas was discovered on the 1st of July 2025 by the Atlas Survey Telescope System in Chile. It was immediately recognized as something extraordinary. This was only the third confirmed interstellar object ever detected by humanity, following Oumuamua in 2017 and to Eoris in 2019.3. The designation 3I stands for a third interstellar object. These visitors are rare beyond measure. The odds of detecting even one such object are minuscule, but we had now found 3, and this third one was about to do something that defied conventional explanation. By late August 2025, the James Webb Space Telescope captured detailed infrared images of 3 Atlas IV. Webb's NASPC instrument, one of the most sensitive instruments ever built, revealed something unexpected. The comet possessed a carbon dioxide gas coma extending at least 348,000 kilometers in radius. That's nearly as far as Earth is from the moon. But here's where the data becomes strange. The abundance ratios of various elements were skewed. The iron to nickel ratios were unusual. The molecular composition didn't quite match the textbook profile of a typical cometary visitor. Then came the anomalies that stopped astronomers in their tracks. As 3 Atlas approached the sun, it began accelerating in ways that defied standard gravitational physics. Harvard's measurements showed what scientists call non-gravitational acceleration. 7. The object was moving faster than the sun's gravity alone could explain. The radial acceleration reached 1.1 times 10 to the negative 6th astronomical units per day squared. The transverse acceleration hit 3.7 times 10 to the negative 7th astronomical units per day squared. To put this in tangible terms, the comet experienced a cumulative acceleration of about 94 kilometers per day squared at perihelion. Think about that. An object already traveling at over 150,000 miles per hour was mysteriously speeding up further. But there's more. Here's where it gets truly strange. The comet was getting bluer. Any astronomer will tell you that comets typically appear yellowish or white as solar radiation illuminates their dust and gas. 3 Atlas was becoming increasingly blue. 9. This suggested an unusual composition, possibly dominated by certain metallic compounds reflecting light differently than standard icy nuclei. Now, the mainstream explanation for the anomalous acceleration was straightforward: mass loss. As the comet heated up, approaching the sun, volatile ices sublimated, shooting jets of material outward. 10. The reaction force from this outgassing could accelerate the comet forward. It's a mechanism called cometary outgassing, and it's well documented. Hall's comet exhibits it. So does the famous comet Neowise. This seemed to settle the matter. Natural comet, natural physics. Except the numbers didn't add up. Between early August and perihelion on October 29th, the mass loss rates of 3 the second. Atlas increased from roughly 330 kilograms per second to nearly 2 million kilograms per second. That's a factor of 6,000 times increase. The comet went from shedding less than 1 million tons per day to ejecting approximately 2 million tons per second. But that's not even the most shocking part. Avi Loeb, the Harvard astrophysicist who has been meticulously tracking this object, began running calculations in early November 2025. 11. His math reveals something that forced him to reconsider everything. At perihelion, the sun delivered 700 joules per square meter per second of energy to 3I Atlas. 12. For a natural comet to sublimate enough carbon dioxide and water ice to produce the observed mass loss rates, it would need to absorb and process an enormous quantity of solar energy. Loeb's calculations showed that the required absorbing surface area of 3I Atlas would need to be at least 617 square miles in diameter. That's roughly equivalent to a sphere 14.3 kilometers across. But here's the problem. The Hubble Space Telescope had imaged 3 Atlas on the 21st of July, 2025, just 3 weeks after its discovery 13. Those images place strict constraints on the nucleus diameter. Based on Hubble's observations, the nucleus could be no larger than about 1 to 2 kilometers across. Think about that discrepancy. The energy calculations demanded a surface area 16 times larger than what Hubble could observe in July 14th. How could a nucleus grow 16 times larger in 3 months without being detected? There's only one plausible explanation that satisfies the physics fragmentation, breakup, explosion. 15. If 3 Atlas was shattered into at least 16 equal pieces, each fragment would have its own surface area. These pieces would collectively provide the required surface area to explain the dramatic mass loss increase. The total surface area of 16 smaller fragments equals approximately 16 times the surface area of a single nucleus. The math doesn't lie. And that calculation comes from one of the world's leading theoretical astrophysicists at Harvard University. Loeb didn't stop there. He released his findings publicly on the 10th of November 2025, stating with scientific precision that the evidence suggests the 3 Atlas may have undergone catastrophic disintegration at perihelion, with the fragments now producing the fireworks we're observing. But that's where the official story starts to fall apart. Because if 3 Atlas simply fragmented like a typical comet nucleus under thermal stress, we'd expect to see a diffuse cloud of debris. Instead, something far more organized is happening, and British astronomers just captured it. On the 9th of November 2025, just 11 days after perihelion, British astronomical observers Michael Butner and Frank Nebling of the British Astronomical Association captured images that changed everything. These weren't casual observations. These were highly processed, carefully analyzed astronomical photographs revealing unprecedented structure. The images show 3 Atlas displaying what astronomers call an anti-tail formation. An anti-tail points toward the sun, which is counterintuitive. Standard comet tails point away from the sun due to solar wind pressure and radiation, but anti-form when specific conditions create a different dynamic. 16. More importantly, Bachner and Nebling captured not just one tail, but multiple distinct jets. 17. The anti-tail jets extended approximately 950,000 kilometers toward the sun, but the longer tail structure was far more impressive. The main columnated jet structure stretched 2.85 million kilometers in the opposite direction. That's nearly twice the distance from Earth to the sun. These aren't scattered wisps of material. They're organized columnated jets, highly directed outflows. The photographs show at least 2 anti-tail jets with Bututner and Nebling, estimating the structures span roughly 30 arc minutes across the sky when observed from Earth. That's equivalent to the apparent diameter of the sun or the moon as seen from our planet. Additional imagery captured on November 8th by astrophotographers M. Jagger, G. Riemann, and E. Prosperberry revealed even more structure. At least 7 distinct jets were visible in their observations, including multiple anti-tail formations. 19. These weren't random jets. They showed organized geometry suggesting a precise directional ejection pattern. And here's the truly unsettling part. When Loeb analyzed these November images, he calculated the mass loss rate being displayed by 3 Atlas. He determined it was ejecting approximately 50 billion tons per month. To maintain that kind of sustained mass loss over the time frame we've observed would require a nucleus diameter of at least 5 to 10 kilometers if it remained intact as a single object. But if it fragmented into 16 pieces, as the July to November data suggests, each fragment would have a smaller nucleus. Yet the mass loss is continuing at these extraordinarily high rates. How? What mechanism maintains such powerful outgassing and fragments that shouldn't theoretically possess this capability? Think about that. Let that sit with you for a moment. Now, the mainstream astronomical community has offered its counter-explanation. Natural comets can fragment 20. It happens. In 2006, Comet 73 P. Schwassmann-Wachmann underwent a dramatic breakup, splitting into multiple pieces. 21 Comet Neowise showed unusual activity. These events occur when thermal stresses overcome the cohesive strength of a comet's nucleus. The sun's heat creates internal pressures that can shatter the object like ice cracking on a frozen lake. For 3I Atlas, the reasoning goes the intense solar heating that perihelion. Despite perihelion being relatively distant at 203 million kilometers from the sun, could have been sufficient to overcome whatever internal cohesion held it together. The material sublimated so rapidly that internal pressures built up and boom, the nucleus fractured catastrophically, except that astronomers who've modeled this scenario are finding inconsistencies. The interior temperature calculations don't quite match the required breakup thresholds. The timescale of sublimation should have been more gradual, and perhaps most troublingly, the jet structures showing such geometric organization in November suggest something more controlled than a simple explosive fragmentation would produce. This is where Avi introduced his most controversial hypothesis, and I'm not going to shy away from it because it's important to understand exactly what he's proposing, even if it challenges conventional thinking. Loeb suggested in his November analysis that if natural cometary physics cannot adequately explain the observations, we must consider alternatives, and his alternative hypothesis specifically addresses the jet's organization and the sustained mass loss rates. What if Loeb posed 3 Atlas isn't a natural comet at all? What if it's something technological? What if the organized jets aren't products of passive thermal outgassing but active propulsion? Now, before you dismiss this as science fiction, understand what he's actually arguing. Loeb isn't claiming proof of alien spacecraft. He's pointing out that the observational evidence is ambiguous. He's stating that certain technological propulsion systems would explain the data more parsimoniously than cometary outgassing. Advanced thrusters operating at high exhaust velocities would require far less mass loss to produce the observed accelerations and jet structures. 22. He wrote specifically that technological thrusters can achieve much higher exhaust velocities than natural sublimation, an alien technology. Employing such thrusters could produce the observed non-gravitational accelerations while burning far less fuel than the mass loss calculations suggest. The required fuel fraction will become minuscule relative to the object's total mass. The geometrically organized jets visible in the November photographs would be consistent with directional thruster arrays. The anti-tail formation pointing toward the sun could represent thruster firing patterns that defy standard cometary physics. But here's the thing. Here's where the academic legitimacy wrapper must be applied. Loeb isn't committing to this interpretation. He's framing it as a question. He's stating explicitly that upcoming observations will determine which explanation holds. He's saying that if 3I Atlas were decimated by the sun and fragmented naturally, the evidence will eventually confirm this. But if it maintains structural integrity despite the extreme conditions and continues producing organized jets, then we'll need to reconsider what we're looking at. And that pivot is crucial because it's scientifically honest. Loeb is acknowledging the competing framework simultaneously. He's not denying cometary fragmentation as a possibility. He's saying that the November observations need further analysis to distinguish between natural fragmentation and something more exotic. Think about what that means for the timeline moving forward. 3 Atlas's closest approach to Earth is scheduled for the 19th of December, 2025.23. That's just 5 weeks away from now. The Hubble Space Telescope is scheduled to perform ultraviolet spectroscopy on 3 Atlas in November, analyzing the composition of its gas emissions and measuring specific elemental ratios. The James Webb Space Telescope has another observational campaign planned for December 2025. After perihelion effects have fully manifested, these observations will be definitive. They will either confirm fragmentation into multiple pieces or reveal an intact nucleus-defying explanation. If Hubble and Webb imaging reveal multiple distinct objects with individual nuclei, fragmentation is confirmed and natural physics suffices. If they show a single intact nucleus producing these extraordinary jets, we enter genuinely uncharted territory. The implications would be profound, not just for astronomy, but for our understanding of what might exist in the interstellar medium. Here's where the comparative analysis becomes essential. We need to contrast 3I Atlas with its predecessor interstellar visitors. Oumuamua, discovered in 2017, showed no COM activity whatsoever. It exhibited no jets, no outgassing, no tail formation. It was essentially a rogue asteroid visiting our solar system briefly before departing forever. The initial speculation about Oumuamua being technologically derived was partly from its lack of cometary behavior and absence of gas jets that would suggest passive thermal processes. Tui Borisov, discovered in 2019, was unambiguously cometary. It showed traditional tail formation, clear outgassing signatures, and behavior consistent with an interstellar comet made of ice and rock 24. It was active, dynamic, and perfectly explicable within standard comet physics. When Borisov fragmented during its passage through our solar system, it fragmented gradually and in ways consistent with thermal stress on a composite nucleus. 3 Atlas occupies an extraordinary middle ground. It's undeniably cometary. The molecular signatures, the coma formation, and the tail structures all point to ice-based composition. But the mass loss rates, the accelerations, the geometric jet organization, and the temporal dynamics are unlike anything observed in standard cometary material. And the pattern recognition trigger is impossible to ignore. We're not looking at isolated anomalies. We're looking at a cascade of interconnected oddities that collectively form a pattern suggesting something unprecedented. The non-gravitational acceleration, the unusual brightening, the bluing of color, the dramatic mass loss increase, the organized anti-tail jets, the fragmentation into precisely 16 pieces. Each data point could be explained, but collectively they form a pattern that can't be a coincidence. As the old saying goes, the missing data trope is also relevant here. Crucial observations remain unreleased or await analysis. Hubble's November spectroscopy results haven't been published. Webb's December observations are still months away from detailed analysis. Amateur astronomical data from the worldwide network of observers continues accumulating. The ISA's Mars Express and ExoMars Trace Gas Orbiter captured images during 3 Atlas's solar conjunction from the perspective of Mars orbit. Those images contain vital data about the object's structure during perihelion, but complete analysis is ongoing. What remains classified or unavailable, we don't know. What observations sit in data archives pending publication, unclear. The fact that 3 Atlas reappeared from behind the sun on the 11th of November, 2025 marks a critical turning point. Now, Earth-based and space-based telescopes can observe it continuously as it moves toward its December 19th closest approach. Here's what's truly unprecedented. This is the first time humanity has possessed the technological capability to intensively study an interstellar object during its passage through our solar system. OMU was discovered well after its closest approach. By the time astronomers confirmed it was interstellar, it was already racing outward at escape velocity Borisov. We detected early enough for some observations, but nothing comparable to what we're achieving with 3I Atlas. We have space-based observatories on multiple platforms. We have networks of amateur astronomers worldwide. We have data from Mars orbiting spacecraft. We have capabilities Oumuamua and Borisov observers couldn't have imagined. 3IE Atlas represents our first real-time intense study of an interstellar visitor, and it's demonstrating behavior that forces us to expand our analytical frameworks. 25. The scarcity principle becomes immediately apparent here. This window of opportunity is finite. 3. Atlas will reach its closest approach to Earth on December 19th, then begin its inexorable journey back into the interstellar medium. The sun's gravity will decelerate it, but not capture it. Eventually, this object will escape our solar system's gravitational influence and resume its journey through the galaxy. Once it departs, we'll never get another chance. The observations we conduct in the next 7 weeks represent humanity's only opportunity to study this visitor intensively. What happens next will determine everything. When Hubble and Webb complete their observations and analysis, we'll know where the fragmentation occurred. We'll know the debris field's characteristics. We'll know the compositional ratios. We'll know the structural integrity of the remaining material. That knowledge will answer the central question driving this entire investigation. Is 3 Atlas a natural comet that underwent catastrophic fragmentation under solar heating, exactly as Loeb's calculations suggest? Is it a fragmented but still recognizable interstellar comet chemically consistent with objects from other star systems? Or does the data reveal something that conventional cometary physics cannot explain? The tribal identity creation matters here. We, you, and we, participating in a genuine scientific mystery unfolding in real time. This isn't a historical analysis of past events. This is live science, active research, open questions, being answered in weeks, not years. By following this story, by understanding the evidence, by engaging with the competing interpretations, you're becoming part of humanity's response to an interstellar visitor carrying secrets we're only beginning to unlock. Think about what 3 Atlas represents. 26. Then, quite by chance, it entered our solar system precisely during an era when Earth hosts a technological civilization capable of detecting it, observing it, and analyzing it. The statistical probability of that convergence is breathtakingly small, and now, as it passes through our cosmic neighborhood, it's either demonstrating a remarkable fragmentation event or revealing something about the diversity of objects moving through the galaxy that we'd never anticipated. Either scenario is profound. The closing window is real. By January 2026, 3 Atlas will be considerably fainter and more distant. By spring, it will be racing beyond the outer solar system toward Jupiter's orbit and beyond. By next year, it will be gone, returning only to the mathematical records and photographic archives documenting this encounter. The data we gather now becomes the permanent record of this visitor. The observations conducted in the next 6 weeks will define what we know about 3II Atlas forever. New technologies might revisit the data with advanced analysis techniques, but no new observations will be possible. The window closes. So here's what remains unanswered. Here's what drives the continued investigation. Did 3 Atlas fragment into 16 or more pieces? Can we observe those pieces individually? Do they show evidence of coherent trajectories suggesting controlled maneuvering? Do spectroscopic analyses reveal isotopic signatures matching known stellar nucleosynthesis patterns? Can we determine whether this object originated in our galaxy or traveled from somewhere even more distant? Most fundamentally, is there any evidence, any signature, any indicator that might suggest this object isn't a natural comet? These questions don't have answers yet. They will have answers in weeks, possibly days. We'll have data that either confirms natural fragmentation or forces astronomers to contemplate possibilities that seemed like pure speculation just months ago. What happens between now and December 19th will either close the book on 3 Atlas as an interesting but explicable natural phenomenon or open doors to reconsidering what interstellar visitors might be. But there's something deeper here. There's a reason this mystery resonates so powerfully. It touches something fundamental about human curiosity. For millennia, we looked at the stars and wondered if anything existed out there. We sent messages into the cosmic void, hoping someone might receive them. We created entire religions and philosophies, contemplating our place among the stars. And now, for the first time in human history, something from the stars has come to us. Not in our imagination, not in speculation, in empirical, verifiable reality, an object we can observe, measure, and study. An object carrying information about distant star systems is written in its chemical composition, an object potentially carrying deeper mysteries in its structure and dynamics. 3 Atlas isn't just another comet, it's a visitor from beyond. And as we study it these final weeks before it departs forever, we're essentially answering a fundamental question. What's really out there? What kinds of objects traverse the interstellar medium? What stories do these cosmic wanderers tell? The observations continue. The calculations proceed. The debate intensifies. And somewhere in the data, in the spectra, in the images, in the trajectory calculations lies the truth. A truth that will reshape how we understand our cosmic neighborhood. The fragments are real. The jets are real. The accelerations are measured. What created them will determine not just what 3I Atlas is, but what stories the interstellar medium holds, waiting for humanity to finally learn to listen.